In this video, we're going to discuss logistic regression, a classification model and why we need it. Knowing the concept of iterative training, it kind of makes sense to try and make a classifier that uses iterative training. How difficult could this be? Well, it turns out this is rather difficult and logistic regression is one of the possible solutions. But first, let's explain why it is difficult to make a classifier with iterative training. Iterative training requires three ingredients: a model class, a cost function, and a way to minimize that cost function. Let's say we're going to use linear models which have linear boundaries to separate the classes. For the cost function, we're going to use the number of incorrect classifications. To minimize it, we're going to use stochastic gradient descent. But this is where the first problem arises. If you think about it, this is not going to work. Please pause the video and take a moment to think about this and why this is the case, and afterward we discuss the answer. Okay, welcome back. The problem is the number of incorrect classifications is obtained by counting, and therefore it is an integer. If we visualize this objective function, it is going to look like this graph. There will be jumps and plateaus. In this case, gradient descent is not going to work because the objective function is not smooth. How can we avoid this? Well, a second idea could be, why don't we just use linear regression? After all, we can train it iteratively, so let's see how that could work. Let's say we use +1 for y to indicate the class A, and we use y equals 0 for class B. Then we train our linear regression model on our data. If the prediction of the model is larger than 1/2, we say it's class A. If it's smaller than 1/2, we say it's class B. This is not a bad idea, but it also has several problems. The first problem is, what if we have 3 classes? Well, we can set y to 0, 1 and -1. But if you do that, the order of the classes suddenly matters. And for classification, we might not be able to order the classes in any logical way. This is only possible for regression. So there is no straightforward extension of this approach to more than 2 classes. There is also a second problem. Let's say we're going to build a model for a bank. We need to predict whether someone is going to pay back their loan or not. For this, we have trained a linear regression model as shown in this graph. People are indicated by yellow dots, where a value of 1 means that the loan has been paid back and a value of 0 means it was not paid back. As you can see, something is going wrong here. Is this regression line really giving us the probability of paying back a loan? The answer is no. The predictions of a linear regression model cannot be interpreted as a probability, because this model can predict a negative number or a value larger than 1. Therefore, these cannot be probabilities. However, a bank would really like to know what these probabilities are of a person paying back their loan. This probability of observing a particular class, given the features, is called the posterior probability. In many cases, this probability is useful to know. This is what logistic regression does. It predicts the posterior probability for each class. This graph illustrates logistic regression trained on our loan data. We see towards the right that the probability is going to 1, and on the left the probability is going to 0. The prediction is always between 0 and 1, as you would expect for a probability. Okay, let's summarize why we want to use logistic regression. Logistic regression uses iterative training for classification. It works well with more than 2 classes. Logistic regression not only predicts the class, but it also predicts the posterior probability for each class.